Hey everybody, this is Kai Werner from Confluent. Today I want to talk about IoT architectures for digital twin with Apache Kafka and MongoDB. So let's get started. Here's the agenda for the next 40-45 minutes. I want to explain what a digital twin is and discuss some use cases about that, and then introduce Apache Kafka and event streaming and why that helps so much with many IoT projects. It's also important to understand how this relates to other IoT platforms and how to use them together, and then to build a digital twin with these combinations, and of course together with MongoDB for having a good storage, for doing analysis and reporting and so on, with this great combination of technologies in an open scalable ecosystem. And finally, I will also show a live demo about a digital twin we've built for connecting 100,000 cars for real-time processing and analytics with Apache Kafka and MongoDB. So let's get started with the introduction about a digital twin and the motivation. So the motivation in the end is pretty simple, because in the IoT space, typically it's really a big shift. Software and digital services become the key differentiator. This is an analysis by McKinsey and Company, but this is a common scenario, and every vendor has to change its business model, right? In the end, it's not just about producing and selling hardware and doing physical services to repair hardware, but it's more about providing additional software to make additional revenue, to make the customer more happy, and to compete on the market. So this is really the main motivation for building a digital twin, to combine the hardware with the software. Here is how it looks like, and it really doesn't matter which industry you're in. So many people think about a digital twin is something for especially manufacturing and production lines, or maybe robots. And of course that's true, but a digital twin is also used in healthcare, and not just for machines, but also for the human body. And is also sometimes used just to improve digital processes, so not even a physical device inside that. So in the end, in short, a digital twin is a living model that drives a business outcome. That's a really, I think, great definition of a general term digital twin. Here's just a few examples, and I don't go much into deep dive, just that you see you can really use it everywhere. So this is a smart infrastructure from Siemens, where they build digital solutions for the entire building lifecycle. So they, in their term in marketing, they call it a building twin, for example. And I think you get the idea. You want to really track the whole building all the time, from the design over construction and operations, but also up to demolition at the end. And you have all this data to monitor it, to plan it, to simulate, and to make the best decisions for the real physical building. A connected car infrastructure is also a common scenario for digital twin, where the car has a digital twin. So each of the hundreds of thousands of cars is a digital twin, so that you know the exact status. And that's one example where Audi has worked together with Confluent a lot to build this digital infrastructure with streaming data from all the cars in real time to the cloud for further processing. And then there's different use cases here, like obviously things like predictive maintenance, where you can send an alert back to the driver or the car if the engine is breaking, or something like after sales, where you want to have a better customer experience. And of course, also increase revenue with that, right? So this is a great example, and this is actually also the demo which I will show in the live demo at the end of the talk. And the last example is about twinning the human body to enhance medical care. This is an example from Philips Health Suite. And this is really to just get the idea, a digital twin is not just about physical devices. It is also about, of course, machines here in the hospital, but it's also about a digital twin of the human body. And no matter if you're in the hospital or at home, depending on your situation and the health, you have maybe devices working with you, but you really track yourself all the time, so that if there is an anomaly with your heart, then you can get an alert or send it to the hospital or something like this, right? So therefore, a digital twin can be really used in any kind of industry for many different use cases. And what's also important to understand, when we talk about a digital twin, of course, it's about a lot of data and typically real-time processing. But AI, or better, not the buzzword AI, but it really, machine learning is really complementary. And in most cases, you combine it with the infrastructure for digital twin. It's a complementary concept because with the flowing data all of the time, no matter if it's sensor or if it's human data, so you always want to do continuous learning, monitoring, and acting. And this is typically done not just by simple business rules, which you can define, but by statistic models or by machine learning algorithms of any kind, like decision trees or neural networks with an autoencoder for anomaly detection or whatever makes sense. So this is just important to keep in mind. And I also will keep that be part of my live demo at the end because it's a so critical part here. So with this understanding about what a digital twin is, let's think about the challenges, because that sounds great, right? But there is a lot of challenges. And here is a picture from automation industry. And this is always the best example I give, because if you're in manufacturing and production lines, then you see a huge difference on the left side between the machines, which are running for 20, 30, 40 years in a factory. And on the other side, the things we are talking here today about MongoDB and Kafka and cloud services, which are here for maybe 10 years now, but they are also changing all the time. So this is something very different, right? And so you have to think about how do we deploy this open and flexible architecture, but let it work together with these machines. And it doesn't matter if you're in a factory or in a hospital or in a building. These guys live for 10, 20, 30, 40, 50 years. So this is a huge challenge, how to integrate these kind of different technologies and a different way of how you have to think about building these products. And with this, a key trend in IoT is the evolution of IT and OT. And this is really converging. And as most people from a conference like MongoDB come off from the IT world, this is about software development, where you typically change things every year and you add new features. Or maybe now with agile developments and A/B testing in the cloud, you can roll out new features every day. And as just explained in the OT world, this is very different. And this is not just different for the hardware, like the production lines or the robots, but this is even true for the software side, like an ERP system or an MES system. Yes, they are also a little bit flexible and you have to change configuration, but the ERP system itself is also running at least for 10 years. So I'm based in Germany, and if I take a look about the SAP systems deployed all over the world, they are still the very old versions, or most people don't use SAP HANA on S4 yet. So this is a migration process which takes 10 years or longer often. So this is a huge challenge to bring in modern software, also especially then with real-time processing and scalability, into this OT world about a digital twin. And obviously with that, so flexibility and scalability are important because you get more and more data and want to use it. But on the other side, that also needs to be somehow combined with a good kind of cost and complexity perspective. Because when you directly go to the vendor of the machines and buy some proprietary software, this can be very expensive. And also, it's not just expensive, but it's also typically a monolith, which is built just for this thing. So it's not really extendable and not really scalable. Of course, if you have a second machine, you can buy a second software installation, but that's not the kind of how we are thinking in the software world today, how to scale things up and how to decouple applications from each other. So that's why we really, especially in IoT, often see the demand for an open, flexible, and scalable platform. I mean, you might guess it. So this is where things like Kafka and MongoDB perfectly fit in. That's what they were built for. They are open, so you can build any ecosystem around that and change things. But they are also scalable, and they are mission critical. So this means, like the things you know from the OT world for 24/7 operations, this is also what you can do with things like Kafka and MongoDB. And no matter if you're running at the edge or on premise, or if you're running in the cloud, or even in hybrid scenarios. So this is the demand we see a lot in many IoT projects, and that's in the end also the intention for this talk here today. So with this motivation, let's now think about what Kafka is and why it works so well in IoT projects. Kafka is an event streaming platform. And even if you know Kafka already, I see many people thinking about Kafka as a messaging layer. So for example, you use it to ingest log data or sensor data into a data lake like Hadoop or AWS S3 for further batch analytics. This is one use case, of course, but it's just really one of small fraction of use cases. You have many, many other use cases instead of just data ingestion. And the reason for that is because Kafka is not just a messaging system, but it's also much, much more. By default, the core of Kafka is also a storage layer. And the huge thing here is that you decouple producers and consumers from each other with that. In an IoT scenario, sensors produce data all the time. And if you add more sensors, maybe like humans or machines or buildings, then they produce more data. And it doesn't matter to them if the consumers of the data are falling behind or if they cannot scale enough, or it takes a week until they can scale. And therefore, with the storage system, you can decouple the producers and consumers. And also you can easily reproduce data. That's also important for many different digital twin use cases, for doing analytics on old data, for comparing data of different machines or systems, and all these kind of things. And also in addition to the messaging and storage, which is the core of Kafka, the open source framework also includes Kafka Connect for integration. So this means that you can integrate with any kind of source and sink. We will use this in the demo, for example, to integrate with MongoDB. And also Kafka provides Kafka streams and other native open source tools like KSQL for doing continuous processing of the data. So it's not always a good idea to first store it in a database and then wait until someone else takes the data and processes it. This is data at rest, and this is sometimes okay for reporting and analytics. And this is also a good use case where you put data into MongoDB and then do something with that. But for many other use cases, especially in IoT world, you want to continuously process the streams of the data for some of the use cases. And this is why this foundation of Kafka with its event log in the middle works so well. Completely decoupled from the producer, each consumer can do with the data what it wants. And one can be a real-time consumer, right? And for example, for predictive maintenance and real-time alerting. And another one could be an ingestion layer into a data store like MongoDB, where you keep the data forever and do analytics on top of that. Kafka was built for scale in the beginning 10 years ago. So companies like LinkedIn use it for really huge data sets. And also at Confluent Cloud, where we run Kafka and its ecosystem as a fully managed service, we have several customers which run over 1 gigabyte per second with one single Kafka cluster. So it's really working at scale. But keep in mind, so Kafka is not just used by the tech giants. I think you know that already. But today, almost every big company has several different Kafka projects for many different use cases. And what's even more important, what I always point out, is that Kafka is not just used for big data. That's what it was built for. But today, I see around 70 or 80% of the projects I do with customers, and I meet around 100 customers a year, is about not so big data. Right? And that's really important to understand. So Kafka is used for many mission-critical deployments, where it's not okay if you lose some data, because it's not just log analytics with Hadoop, but it's more about instant payment platforms or fraud detection, or in the case of a digital twin, about use cases where it cannot be down. Like, think about a digital twin of a human. If you're in the hospital, it has to run 24/7 without data loss, right? And therefore, here's just a few different examples so that you get a feeling about what Kafka is used for and what customers we see at Confluent. And the key message here is really not to think about all these use cases now, but that it's used for many different kind of platforms and scenarios in IoT, but also in many other projects. So really in any kind of industry for the typical values like increasing revenue and for customer experience, or for reducing costs like migrating data away from a mainframe or legacy middleware system, or for mitigating risk like for fraud detection or regulatory things. Or in the case of a digital twin, maybe for reducing the downtime of the production line, or for increasing the health and reducing the risk of the person in the hospital. So there are so many use cases where event streaming in real time at scale is important. And that's actually also the reason why so many people use Kafka in IoT projects. So this is really a summary of the main arguments I hear all the time. Of course, it's a scalable real-time system, but in addition to that, it's really critical that it's up 24/7. And depending on how you deploy it, you can run Kafka with zero downtime and zero data loss, even if a complete data center is down. And this, in combination with these characteristics I explained before, like decoupling the producers and consumers, being able to reprocess the data, and integration to a legacy system and sensors, and big data stores like MongoDB. This is really a huge system, and you can also deploy it hybrid, combination of on-premise and edge and cloud and so on. And of course, it's open, and you can deploy it without any vendor login. And that's really also a huge characteristic if you want to go global in many different countries with different infrastructures. And here again, what's also important, I mentioned this in the beginning, it's important to think about machine learning and how to combine it, because for a digital twin, machine learning is important to really use the data and get value out of that. Therefore, machine learning is complementary. And this is where Kafka fits in again well. So if you think about machine learning, on the one side, you want to ingest data into a data store to train analytic models to find insights with algorithms. And this can be in different areas. This can be consuming the data directly from Kafka, or this can be consuming the data from something like MongoDB with the Spark connector. It doesn't matter where you train your model, but the point is you want to find insights in historical data. And then the second part, you want to deploy this model to a production system. And in best case, in digital twins, in real time at scale. No matter if it's predictive maintenance in the factory, or if it's the human body where you want to act in real time if there is an anomaly. And this is where Kafka fits in perfectly with this real-time event streaming at scale, mission critical, no matter if it's for industrial IoT or for healthcare or other use cases. So what's also important, we need to clarify really, Kafka is not an IoT platform. That's what I really want to point out. So there is things which Kafka doesn't do, like device management or working in unreliable networks or directly connecting to hundreds of thousands of users if you're in consumer IoT and build something like Lyft, which is a big Kafka customer, which connects to millions of users. So there, of course, some kind of proxy or IoT platform or so is combined with Kafka. And therefore, it's important to understand that Kafka is used a lot in IoT projects, but actually it's complementary to other IoT platforms. And there's many IoT platforms in the market. So this is just an example, right? So from 2019, probably in the meantime, you have 1,000 platforms or even more for specific niches or for more general things. So let's take a look at a few of them without going into too much detail. But there is things like proprietary IoT platforms. That's often provided by the vendors of the machines and hardware. Like, as I said, I'm based in Germany, so I know Siemens very well, where you have, for example, S7 semantic PLCs. This is the controllers running in the production lines. And then you have to connect to them from an IoT platform. And guess it, so Siemens MindSphere, the IoT platform from Siemens, is great for that. And the same is true then if you go to GE with Predix and to Cisco with Kinetic and so on. So all of these hardware vendors also have some kind of IoT platform for that. The big limitation here is that they are often a monolith and they are often very complex and very expensive. They're not really what I just discussed with Kafka about building an open, scalable ecosystem. On the other side, you have IoT offerings from the cloud providers. All of them have IoT services in the meantime. And this is not even just cloud services. That's what they focus on, of course, because cloud providers want to get all the data in the cloud to make more money and keep your data there. That's why getting data out of the cloud is typically 10 times more expensive than getting data into the cloud. And that's true for all these providers. But they also have some kind of edge capabilities. Like in this example here, you see Azure Sphere, where you can directly connect to the Azure cloud from something like a microcontroller. But the big limitation here still is that, first of all, you're really locked into a vendor, which is often not really good if you want to be flexible or if you want to roll out globally. And big companies don't use just one cloud. But also, even at the edge, this is not really built for the edge. So if you don't just want to ingest the data into the cloud, but really do processing at the edge, then this is typically not the right solution alone. And then, of course, there's other standards-based and open source IoT platforms. So there's implementations around standards like MQTT, which, for example, HiveMQ is a good scalable solution. They typically focus on a specific topic, like MQTT and HiveMQ. They solve one solution, and that's what they do very well. So MQTT works very well in unreliable networks, and it works very well with hundreds of thousands of connections. So that's a demo I will show later about connecting to cars via HiveMQ and MQTT, because it's a great combination, right? And therefore, again, I want to point out, so with Kafka and an IoT platform, no matter if it's proprietary or open source or standard-based. This is a great combination. And therefore now we have this spoiled for choice for a digital twin. How do we build it? And honestly, there is no best option, right? So it really depends on the use case and on what you want to do. And then you can evaluate what makes most sense to you. Here are a few of the characteristics of a digital twin technology. And so you can think how to build that. And this is actually what I found on Wikipedia from some references. So many people agree on that, while they have different definitions under the hood. But the point is, you need connectivity. On the one side, to the physical assets, like the machines and PLCs, but also to enterprise software, like the MES and ERP system and CRMs, and also, of course, other data storages like MongoDB. Bidirectional communication is very important because you don't just want to do analytics, but also do command and control to send data back to the digital twin physical devices. But then other characteristics are also important, like decoupling and standardizing the interface, like sharing data with multiple agents, often over different infrastructures and even over different regions. It's important to be able to flexible, to adjust the programs and the deployments, no matter if it's just a production line or the overall architecture. And with that, of course, you also want to have a digital traces where you can analyze also historical data, either with batch analytics or with reprocessing the event-based data. And in best case, this is modular, so that you can add new components and remove old ones. This is very important, as you have seen in the beginning, where I talked about industrial IoT, where machines run for 20, 30, 40 years. So it's very important to be open and flexible here. And with these characteristics, let's now take a look at a few options for an IoT architecture for digital twin. One option is, of course, so you just go to the IoT provider of your machines, like example, if you have Siemens S7 and PLCs, then you take Siemens MindSphere for that. That might work if you just want to do IoT integration and create some dashboards or integrate with a SCADA system or something like that. This is one option, but if you take a look at the characteristics on the top right, like being flexible and changing things, and also be modular and integrate with other systems outside this plant or factory, like with the global ERP or system or something like the CRM or other data lakes, then, well, this is a little bit limited in the monolith, and it's really often also complex and expensive to do it like this. And therefore, of course, I mean, you could just outsource the database for the digital twin, right? So something like MongoDB. In this case, so the IoT platform does all its integration with the edge, and then also sends all the data to the MongoDB database for further analytics of the machines there. But still, this is working in some cases, but you don't have the connectivity and the flexibility to connect to the rest of the enterprise and to really decouple the different systems from each other in a modular way. And therefore, a very common solution we see a lot is that you combine Apache Kafka with IoT platforms for the integration with the edge devices. And also you use the IoT platform for doing something like device management. But then you keep Kafka in the middle for decoupling all the other services from the IoT platform, like the digital twin, in this case with Mongo, but also from other consumers, like real-time apps or like a mobile app, or, for example, a CRM system. So in this way, you have a really modular system where you still can keep the data where you need it, like maybe in Apache Kafka just for a day and in the MongoDB forever. That depends on what you exactly want to do. But with this architecture, you're very flexible and scalable and open. And then in some other use cases, we actually even see this kind of architecture where you don't even use an IoT platform. And this is an example where we directly connect to technologies like MQTT or OPC-UA, or even directly to PLCs like Siemens S7 or Modbus or anything like that, with a Kafka connector, and then process data directly in Kafka. And of course, also ingested into something like a digital twin technology. So this was many different options. You always have this spoil for choice, and there is no one single option. It depends on your use case. And with this understanding now, it's also important to discuss the IoT architectures for Kafka and Mongo. So what you see here is a reference architecture which we have built at Confluent with MongoDB together, where you can see how the combination of these two technologies add a lot of value. So first of all, really, it's important to understand this is now open and scalable, but also mission critical for 24/7 deployments. And with this, you can combine the best of both worlds, using Kafka for real-time streaming at scale, and including doing integration to all the sources and the things, and decoupling the systems from each other. But then also integrating with MongoDB as database for the long-term data storage, for doing things like the batch and real-time analytics there, but also integrating with dashboards or maybe even with other BI tools like Tableau or Qlik when you use the SQL interface of MongoDB. So this is really a powerful and great combination. And then you can deploy this in different options. Here's an example where you deploy an edge digital twin. This means you're focusing, for example, on a factory or on a hospital, or maybe just on a few machines running in a hospital or factory. And here you deploy as a single cluster or even a single broker if you don't need high availability in some scenarios, like in a retail store, and build a digital twin just in the factory of the machine. And so this is one example which is pretty lightweight, and you deploy it in the factory for doing real-time processing and storage in the factory. And of course, you can then replicate that and also deploy it in another factory or hospital. But you can also replicate data to another more central solution, like the cloud or a big data center. And therefore, this is another option where you have local processing and storage at the edge for local problems. So you want to keep data locally for things like edge processing and local analytics for doing things like real-time predictions. From a latency and cost perspective, it doesn't make sense to ingest all data into the cloud to do all the processing there. That's, of course, what the cloud providers want you to do, but that's not the real world in IoT. In IoT, you keep the things to the edge where it makes sense, or where maybe you even have to do it from a regulatory or privacy regulation. But also you replicate data to the central cluster, either in the cloud or maybe in a big data center in a region. And there then it's the same story. So you integrate from different edge locations, and maybe they even have different deployments there. So on the top left, this is what I just discussed before. You see one deployment where we have an open architecture at the edge with Kafka and MongoDB. On the bottom left, you see something where maybe in a production line, it's just Siemens in Germany. So you just use Siemens MindSphere at the edge and integrate that via its Kafka connector to the central Kafka cluster. And then you get all this data from the different factories with different technologies into one single MongoDB Atlas in the cloud to do the comparison of the digital twins from the different factories to find out why is this one factory in the US working better than the one in Germany, while the hardware is exactly the same, but under the hood, maybe the temperature in the factory is different or some other characteristics. And this is the main idea behind this digital twin architecture. And then, of course, you can also go more global, and that's what our biggest customers do. And here it's also so important that you are open and scalable, because in different regions, things are different. First of all, good example from the beginning was Audi, where they started rolling out a connected car infrastructure in Germany. They started ingesting the data via proxies into a Kafka cluster in AWS. But they knew from the beginning that they will also roll this out to China. And in China, there is no AWS. So you have to go to something like Alibaba Cloud or your own data center. And with this open architecture, you can build one template of a digital twin architecture and then deploy it in different regions, either in different clouds or maybe in one region just in a data center. And so this is pretty powerful, and therefore you can either just roll it out in different regions, or then, of course, also replicate the data between different regions for aggregation scenarios and analytics of all the data. So with this overview about different IoT architectures, I want to conclude this session with a demo about a digital twin which we have built for 100,000 connected cars. So intentionally, we wanted to do a real scalable demo, not just Hello World. And here it looks like a lot of components, right? So let's quickly walk you through this. On the left side, we have the cars, the simulated cars, obviously, as we have 100,000, which produce data continuously and ingest it into the Kafka cluster. And from here, then, we do first real-time pre-processing at scale. In this case, we're using KSQL. And that's Kafka native technology, so you don't need another processing unit like Spark or Flink. You can run it just with Kafka if you want. And then we also do the model training just from Kafka data with TensorFlow and TensorFlow IO's Kafka plugin. So of course, you could also ingest the data into a data lake like Hadoop or maybe Mongo to put some MapReduce or Spark ML on that. But in this case, we simply train the model directly from the Kafka data. And then we deployed it to a Kafka application for real-time scoring. And this is really important. No matter where you train your models, which is typically more like a batch mode, the model deployment and scoring and monitoring, that has to run in real time. And that has to run at scale for a connected car infrastructure for, in this demo, hundreds of thousands of cars, but in the real world, even millions of cars. And in parallel to that, however, we also ingest the data into MongoDB. In this case, we want to use it there for analytics and dashboarding so that we can analyze the different digital twins from all the different systems. And this is really a huge scenario which adds so much value. And in the same way, of course, you could combine this on the left side with some proprietary IoT solution at the edge, like Siemens MindSphere in the examples I discussed. So this is the example, and now let's walk through this quickly. I will only do a 5-minute demo. If you want to see a longer demo of that, you can also check the YouTube channel or my GitHub, where I have a 25-minute recording. So the first thing we are doing is I'm starting some test generators. So this is a tool from HiveMQ which simulates 100,000 connected cars. And this is by far not the limit, right? This is just that we have a good scalable demo. But we could also start millions of cars and also process that data in real time with Kafka. So we have running this on Google Cloud in our example. And as you can see here, we are running on Kubernetes. And this is intentionally so that we show that this can be a template framework, like in the example of Audi, which we can roll out everywhere, right? And be very flexible and adjusted like we need. And in this example, I have a distributed Kafka cluster running with 3 brokers and 3 zookeeper, and some add-ons like a schema registry and KSQL. And also important, I have 2 Kafka Connect instances because I have deployed the MongoDB connector there to do a scalable and robust integration in real time into MongoDB, where in this case, we built this digital twin, right? So with this getting started now, let's take a look at the UI. And now here you see a dashboard where it's important to understand this is where we ingest the data. So at the top right, you see we have now 100,000 connections. And these are producing 10,000 messages per second. So this is not much, but this is the real world. In connected cars, it's expensive to send data over 4G or something like that. So each car sends data every 10 seconds. But you can see this is really still big scale because it's coming from a lot of devices. And now we want to process the data with Kafka. So what we're doing here, first of all, we have the raw JSON sensor data in here. So this is coming from the cars, right? So as you can see here, and this is the data we use later, like the engine vibration amplitude. So this is the values which we use to detect the anomalies with our, in this case, model, which is an autoencoder. We ingest all this raw data in JSON, but for further processing and for other reasons, we want to get the data into Afro format. So this is better compressed, and this allows schemas and versioning and so on. And therefore, we have built a KSQL query and deployed that, which in the end is doing one single query where we do processing of the data in real time at scale. So while this is just a SQL query, you can deploy this to production and run it at scale for millions of events per second. And so with that, we transform the data into Afro format. This is what you can see here. So the data is more or less the same. So we didn't do any ETL here. But the big point is now we also have a schema for that. So with that, now we can ensure that the rest of the platform integrates well with this. And this can be the MES system, this can be a CRM system, or this can be our digital twin, which is then also MongoDB, where we ingest the data. So before that, we also want to do some real-time scoring. So that's, in this case, part of the use case, predictive maintenance. And in this case, you see a digital twin can be many things. So it can even be spread out over different technologies. Like we do the historical analysis in long-term storage in Mongo, but the real-time scoring with Kafka native technologies. And therefore, what I'm now doing is starting a model prediction. So what I'm doing here is I deploy a new application, in this case, again, on Kubernetes. So don't be worried if you don't know Kubernetes well. But what I'm doing under the hood is I'm deploying a Python application. So I can show you if you're from the space. But this is in the end one deployment, which is a TensorFlow application with deploying an autoencoder. And the big point here is really that this is, in this example, just a very lightweight Python app. So this means that in this case, I'm not even using something like Java, but a data scientist can just use the TensorFlow Python API and the Confluent Python Kafka API to produce and consume data in real time and build a pipeline around that and even deploy these models, because as it's using Kafka under the hood, it's highly available and scalable, even if it's just Python containers. But you can still scale them up without downtime and data loss and all these things. And now here you see this is model predictions, and these are also coming in real time on the pipeline we have built. So in this case, what we have done is we have built one single pipeline for model training, which is batch, for model predictions, which is real time, both Kafka native. And we are now also ingesting the same data into MongoDB for long-term storage and further analytics. So therefore, if we now take a look at MongoDB, and I have in the end created one collection here, as you can see, which is, I call it digital twin. So this is now the sensor data. In addition to doing the real-time processing and scoring in Kafka, we are storing all these events also in MongoDB. And with this now in MongoDB, of course, you can use all the features, which for you as guys from the MongoDB conference, you know MongoDB well, so I won't focus on that too much. But the point is now you can do anything you want to do with MongoDB, like creating dashboards, integrating with BI tools, doing further processing in ETL here with the data, and simply keep it long-term for storage for doing further analytics with that. And that's really huge. And then, of course, you can also send it back to Kafka, like with Change Data Capture, which is available as a Kafka connector. And with this combination and end-to-end deployment, I think it's really huge. So, and let's recap here. So we have really built a highly available and highly scalable digital twin for real-time processing of millions of events with Kafka native technologies and with long-term storage and analytics capabilities with MongoDB. And I think this is really a great example. And you can also check this out on my GitHub page. So to recap and think about the key takeaways, with Kafka and MongoDB, it's really a great combination. So we can easily build digital twins to merge the physical and digital world. But also, as you have seen, this is really open and scalable and flexible. And this is really important for IoT, where you on the one side have machines or devices which are sometimes 20, 30, 40 years old and often use proprietary technologies. Or maybe you have to put a Monolith IoT platform in the middle. But then to integrate with the rest of the world and to do data analytics, you use these open platforms. And this is both for event streaming in real time and for long-term storage analytics. And that's why Kafka and MongoDB is such a great combination. And then especially because with this, you can deploy this at the edge or in the big data center or cloud, or even hybrid. What actually, to be honest, in most IoT scenarios is the case, where you deploy things at the edge and in the cloud. And then often even multi-cloud or over different regions or even over different continents. This is what our biggest customers do. And so with this, I hope I gave you a good overview about IoT architectures and how to build a digital twin with Kafka and MongoDB. If you have any more questions, please connect to me on LinkedIn. So that's also best to keep updated in the future. Or feel free to connect to me via Twitter or via email. So thanks a lot for watching and have fun with Kafka and MongoDB.